All right, today we're putting on our detective hats to solve a really frustrating mystery in the world of edge AI. It's a classic case, you know? It starts with a super powerful, tiny computer, a cutting-edge AI model, and one very, very cryptic error message. So let's take a look at our first piece of evidence. And here it is. This is the villain of our story. I mean, look at that thing. Unable to allocate CUDA 0 buffer. It's the kind of error that just stops a project dead in its tracks, right? This popped up for a user named William over on the NVIDIA developer forums. He was trying to do something that honestly should have been pretty simple, but his little computer just flat out said, nope. And this is the clue that kicks off our entire investigation. And that really is the central question, isn't it? You've got this incredible device, a Jetson Orin Nano. I mean, it's a tiny little beast, packed with over 1,000 CUDA cores, literally designed for this exact kind of AI work. And yet, you go to run a single model, and bam, you hit this brick wall of an error. The promise of powerful local AI is right there in your hands, but the reality, well, it's a lot more complicated. So what is really going on here? Okay, so to solve this mystery, every good detective knows where to start. You round up the usual suspects. And in the world of edge computing, when a model just refuses to load, there's a pretty standard lineup of things that could be going wrong. We've got to check them out first. So, pulling from the suggestions on the forum, the checklist kind of looks like this. First, is there even enough memory? Okay, what about the power mode? Is the device getting enough juice to actually do the work? Then you think about software. Is Jetpack up to date? Or maybe, it's too new and something broke. And of course, could the AI model itself, even if it's supposed to be a small one, still just be too big for this device? I mean, these are all classic reasons for failure on these tiny, resource-constrained computers. And William, our user, he checked every single one. And guess what? None of them were the problem. Yeah, and this chart really puts those hardware limits into perspective. Look at William's device, the 8GB Orin Nano. It's powerful, for sure, but you put it next to a slightly beefier 16GB model, and you can really see where the limits are. You've got less memory, a lower top speed. I mean, these little devices are living right on the knife's edge of performance. But here's the thing, even with those constraints, this simple task should have worked, which just made the mystery even deeper. So after going through all the typical troubleshooting steps, checking the power, the memory, the model size, the case pretty much went cold. The evidence just wasn't adding up. And then, a breakthrough. A comment from an NVIDIA staff member on the forum revealed a twist that, honestly, nobody saw coming. So after all that debugging and all that troubleshooting, what was the real issue? What was the one simple thing breaking everything? It was a bug. A known regression in the software. That's it. It wasn't William's fault. It wasn't the hardware. It wasn't the power mode. It wasn't the model he was using. It was just a plain old software bug. So, case closed, right? Well, not exactly, because this reveal actually opens up a much, much bigger conversation. Because here's the secret. Even when there isn't a bug, running AI on the edge is just fundamentally really, really hard. So let's zoom out a bit. That bug, it was just a symptom of a much larger challenge. The real story here is about getting multiple, complex AI models to all play nicely together on a tiny, power-sipping device. And that is genuinely one of the biggest challenges in robotics and AI today. This right here, this is what developers are constantly up against. It's a non-stop balancing act. You've got latency. Can the model respond fast enough for, say, a robot to not run into a wall? You've got power. Can it even operate within a super tight 7 to 25 watt budget? Then there's memory. How do all your models share this one tiny unified 8GB pool of RAM and VRAM? And finally, reliability. What happens if one model fails? Does it take the whole system down with it? It's a constant high-stakes juggling act. So, how do the pros actually manage this insane juggling act? Well, it turns out they have a toolkit of architectural strategies designed specifically for this kind of environment. So let's take a look at the 3 main approaches for taming the beast of multimodal AI on the edge. All right, the 3 big ideas are these. First, there's partitioning, which is basically slicing up a pie for each model. Then you've got prioritization, which is like creating a VIP line for your most important tasks. And finally, offloading, which is pretty much what it sounds like, calling for backup when the job's just too big. Okay, let's dig into partitioning first. The whole idea here is to build walls. You use tools like CUDA green contexts or Linux C groups, which are basically just ways of telling the operating system, hey, fence off this specific chunk of resources. You reserve a fixed piece of the GPU or memory for each model. And in theory, it's great. It guarantees that one model can't step on another's toes, it's supposed to be clean and predictable. But, and it's a big but, here's the catch. On a tiny device with unified memory and a super tight power budget, these rigid walls are just incredibly inefficient. Think about it. A model might only need its reserved resources, say 10% of the time. That means for the other 90% of the time, that hardware is just sitting there, doing nothing, completely idle. Imagine you reserve half your GPU for a camera model that only needs to run once a second. That is a huge waste of power and performance that another, more critical model could be using. So this approach, it often just makes the bottlenecks even worse. So that brings us to our second strategy, prioritization. Now, instead of walls, I want you to imagine a shared workspace, but with a very, very strict manager. All the models get to share all the resources, but you have an event-driven system that acts like a traffic cop. It's constantly making sure that the most critical tasks, like, say, a robot's main control loop, always get to go first. This is the exact approach used in some really advanced robotic systems. And the real beauty of this approach is its flexibility. It's super efficient because no hardware is just sitting idle. And it allows for something called graceful degradation. So, for example, a robot's critical obstacle avoidance system, it always gets the resources it needs, no matter what. But if the whole system starts getting overloaded, a less important task, like maybe its friendly wave animation, might get a little choppy. And that's a smart, safe trade-off to make. The downside? Well, it's definitely more complex to program, and you still have to be careful that your models don't interfere with each other. And that brings us to our third and final strategy, offloading. This one asks a really simple question. What if the best way to run a huge model on an edge device is to just not run it on the device at all? Yeah. With this approach, you send all the heavy computational lifting to a much more powerful computer nearby, or to the cloud, and your little edge device just handles the simple inputs and outputs. I mean, the upside is huge. This gives you practically infinite power and completely eliminates any resource fights on your edge device. But the downside is massive. It is completely 100% dependent on a fast and reliable network connection. So think of a delivery robot in a city with great 5G coverage. It works perfectly. But the second that robot enters a parking garage or a network dead zone, its brain is effectively disconnected. It could become totally useless. That connection drops, and your super smart robot, well, it suddenly isn't so smart anymore. Now check this out. This data from a recent research paper really shows just how complex these trade-offs can get. So common wisdom says that if you optimize a model using something called quantization, which is basically just making it a bit less precise to save space and hopefully speed it up, it should run faster. But look at this chart. For the smaller models, the optimized version on the left is actually slower than the unoptimized one on the right. It just goes to show you there are no easy answers here. A flexible architecture is absolutely key because every single choice you make has to be carefully tested for your specific situation. And this chart really drives that point home. It shows the peak memory usage for different models across the entire family of Jetson Orin devices. Now, look closely. For any given model, the amount of memory it uses is almost identical, whether it's running on the most powerful, top-of-the-line AGX or the tiny little Nano. And what does that prove? It proves that you can't just throw more hardware at the problem and hope it goes away. Smart software architecture, like the prioritization or offloading strategies we were just talking about, it's not just a nice-to-have. It is an absolute necessity. So we started with a single, annoying error message and ended up looking at the grand challenges of Edge AI. Let's boil all of this down to the one key takeaway for anyone out there who's building the next generation of smart devices. So what's the winning strategy today? Well, the one that's been proven in real-world robotic systems is all about flexibility. You want to avoid building those rigid, inefficient walls with partitioning. Instead, you should favor dynamic, event-driven systems that can adapt to whatever is happening and always prioritize what truly matters in that exact moment. It's all about intelligent sharing, not strict division. And that kind of leaves us with one final thought to chew on. You know, our hardware is getting smarter and more powerful every single year. Our AI models are becoming almost unimaginably capable. But it really seems like for every single new capability we gain, our ambition for what we want to do with it grows even faster. And it's this constant tension, right? This push and pull between our imagination and our hardware's limits. That's what's going to keep driving innovation in this space for years and years to come.